So in this video we're going to continue our study of how to find the area underneath a curve. So recall last time that we were looking at this function f of x is equal to negative x squared plus 16, and on the left is one way to approximate the area. So our goal is the area between the green curve and the straight axes there. And what we did is we broke it up into 4 rectangles, and we said, well, if we wanted to approximate the area, we could compute the areas of these rectangles. You know, this first one is 16 by 1, plus then it looks like we've got 15 by 1, plus I think we said 12 by 1, plus finally 7 by 1. And we end up with an approximation of the area that isn't so bad. It's 50. It's not terrible. Well, the problem is that it's not exact, it's not great, and so if we want to get a better estimation, the problem is we have to redo all our work. If we're going to do this by hand, we got to look in here and make more rectangles, and we see, well, now we have a rectangle that's still 16, but it's only half an unit wide, plus the next one we measure very carefully, we get 15 1/4 times a half, plus we keep doing this, and we get a better estimation. The problem is it's still not great. What we want to do is we want to get as close to estimate as we want as possible, and we want to avoid doing this work of measuring and computing all of this stuff. And so that's what we're going to do in this section, is really find a nice slick way to compute areas without a lot of work. Well, with less work than you'd have to do it if you tried to sit down by hand with a ruler. It's still going to be a bit of work. We can't avoid it. So there are many different ways we could proceed now in terms of dividing up this area that we want to figure out into rectangles and figuring them out. We're going to go through 4 different ones. There's many others. They're all just as good as each other, but we'll just go through them all for the sake of completion. So the first thing we want to talk about are upper sums. So what you do is you figure out an area that you want to compute. So we'll use this area in here between the graph that's in green and the black line at the bottom and this dashed line over here. And the first thing we'll do is we'll divide it up into a space of, we'll go with 5 rectangles. And we'll say we want to compute first, we'll try to find the upper sums. So what the upper sum means is that you look at your first interval here, you find the highest point on the interval, and that's where you build your rectangle. So here this first rectangle is about 3 high. Then you go to your next interval, you find the highest point, and you draw your rectangle there. Now with the third interval where it gets interesting is that your highest point is again going to be over here. For your fourth interval, let's see, it looks like the highest point is around there in the interval. And lastly in our interval, it looks like we'll make a last rectangle. So in the upper sum, the key is that all of your rectangles are above. And so it's nice because it gives a nice overestimate. It always gives you a little bit too much of your area. We can also go ahead though and compute lower sums in a very similar way. So what we do is we go through and we break up our interval into pieces here. So we're going to make 5 rectangles, and instead we pick the lowest point, and that's where we draw our rectangles instead. So we draw all of our rectangles will end up being below our curves, because we always just pick the lowest point for our rectangles. And in this way what we're going to get is we're going to get a nice undersum when we go ahead and we compute the area down here. So upper sums always give an overestimate, lower sums always give an underestimate. The problem is that it takes a lot of work because you have to really look at your function carefully to figure out exactly what point this is going to be. Instead, what's nice is to use what are called left and right sums. So left and right sums we've already seen, but we'll review them again, just the idea of them. So over here in the left sums, what we're going to do is for our interval, we're always going to use the left endpoints for our sums. And now what's going to happen here is we're going to see that this isn't necessarily, even though this is a bad drawing, going to be always an over or an underestimate. We're going to overestimate in some places, we're going to underestimate in others, so it's not going to be an over or an underestimate, it's just going to be an estimate. And similarly with right sums, which are my particular favorite, is what we'll do is we'll always use the right endpoint of an interval to draw our rectangles. So we'll just go up on this right endpoint. Wherever it hits our graph, that's where we'll draw our rectangles. And so once again, some parts are overestimates, some parts are underestimates. Overall, the idea is that we're just going to make an estimate overall. So none of these are really better or worse than any others. They all provide estimates, and they all become more accurate as we use more rectangles. So our goal here is to systematically build up right sums so that we can compute them easier. So we're going to start by saying, suppose we have this function f that's going to be continuous on the interval a to b. So this is a nice continuous function, no breaks, no jumps, nothing. And what we want to do is we want to make a whole bunch of rectangles here in a nice systematic way so that we can go through and compute them all. And I will just draw them in here quickly for the sake of completion. And so basically what we want to do is we're going to go through and we're going to make n rectangles, and we're going to call each one r sub I. And so what we want to do is we want to take and we want to add from 1 to n the areas of all of these rectangles. And so what we need to do here is we need to figure out the height of each rectangle and multiply it by the width of each rectangle. And so what we're going to do is we're going to do this in a certain way, so we're going to say that all widths are the same to make our lives easier. What we really want to do is we really want to break this up so that every single width is the same, and we're going to call that width delta x. And we want to figure out our heights. Well, the height is just going to be in terms of something about the function. That is, if we look here, well, the height needs to be a point on the graph of the function. So in this way, we're going to be able to compute these things as long as we can find a way to make sense of this pattern right here. And we're going to work through a way in order to make this pattern work out nicely for us. So now we've got this all cleaned off so that we can work on stuff. So the first thing we want to figure out is how to make sense of this idea of the width of a rectangle. Well, what we've got is we've got this interval from a to b, and we want to make n rectangles in it. So what we need to do is we need to divide it into n pieces. And so the easiest way to do this is to say that the width of our rectangle, which we call delta x, is going to be equal to b minus a, which is just the length of our rectangle, divided into n pieces. So n is just a nice positive integer. And in this case, we're not going to say what number it is yet. So what this does is this means that we've now broken this up into a bunch of different pieces. So I'll draw them in here, of course. And so this one has delta x wide, this one's also delta x wide, this one's delta x wide. They're each going to be delta x wide, and we've got n of them. So if we add them all up, we take n times delta x, which is going to be equal to n times b minus a over n, which is just going to be equal to b minus a, the length of our interval. So now that the width problem is figured out, we also need to figure out how to figure out the height of each individual rectangle. So let's look at this here. What we're going to do is we're going to start at the point A here, and we're going to draw a distance here of delta x, and this is going to be the width of our rectangle. And if we draw on a rectangle, what I want to do is I always want to use the right endpoint. That is, to make my rectangles, I'm always going to move over a distance of delta x. I'm going to go up to my graph, and that's going to be the height. And so I can just keep repeating this over and over again until I get to the end. And so what we have here is we have a series of points. And what I want to do is I'm going to give them names. What I'm going to say is this point right here is going to be x1. So right up here on the line, it'll be x1. And x1 is equal to a, my starting point, plus delta x. I moved over one space. Next here, I have a point which I'm going to call x2, another endpoint of my interval. And what this is going to be is this is just going to be x1 plus I moved over another delta x, which means this is a plus 2 delta x is moved over. So next what I've got is I've got another endpoint now for a rectangle. And in this case, this rectangle's endpoint will be x3, and that's just a short way to say a plus I moved over 3 widths. And in general, xi, any endpoint, will be a plus I times delta x. This tells me how many widths I've moved over. So let's look at what I've done so far. Again, this first starting point will be x0. Then I've got another point x1, another point x2, another point x3, all the way down until I get to my final point at B, which is also going to be called xn, which will be a plus n times delta x when I moved over all the way to the end. And from this, what I can do is now I can figure out the height of any rectangle. So the height of my first rectangle will be the value the function takes when I put x1 into it. So that is, this height is f of x1. The second rectangle will have height f of x2. The third will have height f of x3, and so on. So now what I've got is I started with this idea that I want to add up these rectangles, their areas, and what I can do is I can represent these areas as a height f of xi times a width delta x. And so now what I have is I have a really nice pattern that lets me compute the right sum approximation for this function. And so sometimes what this is also labeled as is we label this r sub n of f. So this is a fancy way to say right sum. We're going to use n rectangles. And finally f is my function. And so whatever number this ends up being is my approximation. So let's look how this works with a real function. So let's look how this process works for the function f of x equals negative x squared plus 16 on the interval 0 to 4. So the first thing we want to figure out, step 1, is we want to figure out delta x, that is the width of our rectangles, and this will always be b minus a over n. And so in this case, what we have is, if we look over here, we have a b equals 4, and we have that a equals 0, and n will just be very abstract. So in this case, our delta x is going to equal 4 minus 0 over n, which simplified down becomes 4 over n. The next step in our process is to figure out the height of a rectangle, and for this we need to figure out our endpoints. So each endpoint xi is given by the formula a plus I times delta x. So in this case, our xi is going to be our a value, which was 0, plus I times our delta x value. And our delta x value we figured out above is going to be 4 over n. And finally, the actual height will be given by f of xi. So this is our actual height function. So finally, to figure out the sum, what we have is we have that r sub n of our function f is going to be the sum from I equals 1 to n of our function at this endpoint, that is the height, times the width delta x. And then of course we want to replace this actually with our stuff. So this was very abstract, so let's replace it with our function. So again, we have the sum from 1 to n. Now we have the function f, and we're going to put into this function our xi. So this is 0 plus I times 4 over n, and we're going to multiply it by 4 over n. And then we can always go one step further and make this look like f. The sum from I equals 1 to n of, in this case, we're going to put the 0 plus I 4 over n into our actual function, which we gave way up here in the corner. And so this is going to be the function negative, in parentheses, I times 4 over n squared plus 16, the whole thing times 4 over n. And now what's nice is now this sum is something we've seen before. We worked the other day about how once we've gotten to this point, what we can do is we can use our properties to simplify, break this thing up, and actually figure out what this is going to equal. And what's nice is that this is a formula that'll work for any n. Suppose you wanted to use 10 rectangles, then you can use n equals 10. Suppose you wanted to use 100 rectangles, n equals 100. Suppose you wanted to use 1,000, go ahead and use that. This formula will always compute those. So what I have here is I have an image that shows our graph, and in blue we've got right sum rectangles, and in red we have left sum rectangles. And we can see with 4 rectangles we obtain an approximation. The blue is an overestimate, the red's an underestimate, and both of them have a good amount of error. So what we can do is we can increase our rectangles. So now here instead what I've got is I've got 8 rectangles. Once again, blue are right sums, red are left sums. And what we can tell visually is it looks like a bit better approximation. It's pretty close to the curve now. There's still error present, but it's not as bad. And so what we can do is we can do this more. So here I even have 100 rectangles, and what we can see is this is getting really darn close, right? It's really actually hard to see. You can faintly see that the blue rectangles still overestimate a little bit, but it's not much. They've gotten really small, this error. And so this happens no matter what you use, left sums, right sums, whatever. It turns out it's always going to be a better and better approximation the more rectangles you use. And now finally, all the work we did with limits is going to pay off, is the fact that there's a big theorem here that says that if f is a continuous function, non-negative on this interval, then the limit as n approaches infinity of right sums, left sums, upper sums, lower sums exist, and they're going to be equal to each other. So what we can do is we can take the limit as n approaches infinity of this really abstract looking computation here, and when we're going to get a really great approximation. We're going to figure out the area. So we have to say thanks, limit man. So this is so important that we're actually going to make this the definition of the area of a region in the plane. That is, if you have a continuous function, non-negative on an interval, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is going to be given by finding the limit of this expression you found. So what we really want to do is, this is just the right sum expression again, but we want to think about what this means. So the definition has several parts. So the things to think about are remembering that f of x times I gives the height of a particular rectangle, delta x gives the width, multiplying them together gives the area of a rectangle, the sum symbol says add them up, so that the total amount is an approximation. So that is, these symbols right here, the inner part with just the sum, is an approximate area. And what the limit part says is, it says build a better approximation by using more and more and more rectangles. And what it actually does is it gets you the best version. It gets you close to the answer, and it actually gets you the exact answer. It'll actually figure out the exact answer if you're capable of doing all of this work. So let's see how this works. So here's our example that we've been using again and again. We want to start with the function f of x equals negative x squared plus 16, and we want to find the area bounded by the graph of f, the x-axis, and the lines x equals 0 and x equals 4. So again, we have the same basic setup. We're going to have delta x, that is the width, going to be 4 minus 0 over n, so 4 over n. Our points, xi, will be our starting point, a plus I times delta x. So in this case, we're going to have 0 plus I times 4 over n, which of course you can just simplify down to I over 4 over n. And then we need to put this all into our limit definition. So this means that area is going to be the limit as n approaches infinity of the sum from I equals 1 to n of f of xi times delta x. And so putting in our particular information from the function yields the following. And so it's important to note that the 4 over n came from delta x right up here, and that the x sub I that we're putting into our function came from our calculation up here. And so now what we want to do is we actually want to put this into the function. So now using our function f of x, we replace all of our x's with 4 over I n squared and have the 16 in there. I like to use brackets to keep everything organized. And so what we want to work on is we want to work on solving the sum first. So we usually work from sort of the inside out. And the thing to notice is we have this 4 over n here, and since it's being multiplied, what we can do is we can factor it out. Now after factoring it out, what we want to do next is we want to look and think, well, what are some things we can do with sums to make this thing easier? And one of the things we remember is that since we have an addition in here, we can break this up into separate sums. Now I've also done 2 steps here. I've not only broken it up into separate sums, I went ahead and multiplied this out, squared everything. So that's how I got the 16 I squared over n squared by just multiplying it all out. Now another thing to note, this sum has become really nice. This fits our formula here. Whereas this first sum, what we need to do is we need to factor out the n squared and the negative 16, so we're just left with I squared, once again a sum we're able to compute. So as you can see, I've run out of room here. These do take a bit of work to get through. So what I'll do is I'm going to clear this off, make some room, and restart over. But I'll copy this last step over to the top. This would also be a good time to pause the video, copy some things down into your notes as we keep moving. So now we've come this far in our sum. Our goal is to compute some area, and we've done a few steps in between so far, and we've got this step here. And now our goal is, again, we just want to factor some things out so that we can get down to sums that we can compute with our shortcuts. And so what a beautiful sum this is. We're now down to 2 formulas that we can use our formulas that we know from sums in order to compute these much quicker, because we've got pretty simple looking things now. And so now, after using our formulas, the thing to note that's neat is so far we have actually removed all of these sigmas. So we've removed the sigmas. So this is a really good step to have accomplished, because now that we've removed all the sigmas, well, we're back into stuff we learned a bit ago, section 4.5. We're now computing infinite sums. Okay, we want to figure out what happens as n approaches infinity, and the first thing we should really do is we really need to just multiply everything out. And so the first thing I did was I took this 4 over n term and I distributed it to both terms here, multiplied some things out, and got what you see in front of you now. And now what we want to do is we want to multiply this first term out a little bit more to see what happens. Because the 64 is in good shape, but the rest of it still isn't quite easily computable yet. So, after a little bit of algebra here, and for some reason the 64 got cut off on the end, what we've got is this term to compute now. So now we want to think back again to our limit properties, and we want to think about what's going to happen as n approaches infinity. So the key here is to look and see, well, we have an n cubed in our denominator. The largest term is n cubed in our numerator. So this means as we approach infinity, we remember by rational functions, these 2 terms don't really matter anymore. What's really the big deal is really looking at these and thinking about our leading coefficients. So what happens when we compute the limit is this means we're going to get negative 128 over 6 plus 64, which we run it through our calculator, and we get, and we're going to get 128 over 3. Now a big thing to remember is that this 64, since it doesn't have an n in it, well, as n gets bigger and bigger, it's unaffected by it, so that's why it just comes down as 64. So this means our final answer, our area underneath this curve, is 128 over 3 as a fraction. And so this is a number that would be very difficult to just measure by hand, or even use a few number of rectangles to realize that this is what the answer is going to be, but using this process is really neat. We ended up using an infinite number of rectangles to compute the area, and we did this without doing an infinite number of work. I'm not going to disagree that there's a large number of steps here to follow. So what I'd like you to do, in addition to the problems I've posted on Blackboard, and in addition to writing a question, which I think most of you will have the same question, do we really have to do this all? Yes, the answer is yes. I want you to repeat this process for the function f of x equals 4x plus 3 over the interval 1 to 5. Also, just so you know, the answer you should get, if everything goes smoothly, is 60. Finally, I want you to try drawing the graph and thinking, is there a different way to find the area of this function that wouldn't involve doing this whole process? So try to find another way in this case. But as always, if you have any questions, go ahead and email me, stop by my office hours, or of course ask in class. Thanks.